Alright, so now let's talk about Euler's problem, Euler's buckling load. And he wanted to calculate, when the column buckles. Okay, so here let's consider a simply supported column, and then at point B, so we have a compressive load. Okay, as I told you, this is completely one-dimensionally loaded member. Then we can calculate the stress by dividing the load P by the cross-section area. But everybody knows that, at a certain point of load level, and that the column buckles in the lateral direction. Say we have some positive displacement here, okay? And then to investigate this problem, he formulated a governing differential equation. Say once we have a curvature, then the internal bending moment can be calculated by the well-known flexor formula, the flexor rigidity, and the second derivative of the deflection. Maybe some students may be very curious why we have this positive bending moment rather than the negative bending moment, because we have this negative curvature here. All right. The reason is, because we show the boundary condition for this problem. That's why it looks like that. But in general case, let's say we have positive displacement, and then positive curvature. This is my general discussion, isn't it? Generally speaking, we have positive curvature, and then multiply to the positive curvature, we need to consider the flexor rigidity, and that's the bending moment, isn't it? And then if you imagine the force P here, the force P produce another moment. So let's consider the sum of moment. Let's consider the force equilibrium for this remaining body. And then I want to consider the force equilibrium with respect to point A. Because this is simply supported at point A, the moment in the sum of moments should be equal to 0. Say I have one bending moment, the plus. And then the bending moment produced by the external load. And because we want to consider this a small deformation problem, P, and then we have deflection V is equal to 0, isn't it, right? And then instead of bending moment, I want to plug in the flexor rigidity, and then the second derivative of the deflection. As I mentioned here, so let's divide P by the flexor rigidity. Now, to emphasize, this is positive quantity because I want to consider the P is positive quantity, and instead of P over flexor rigidity, I want to put K square here. Then I have the mathematical equation. So once we have a buckling, then this governing equation must hold. So which means if we can find any non-trivial solution to this governing equation, then we can say that this is the beam buckles by the compressive load P. You understand? Okay. So this is nothing but just second order ordinary differential equation. The general solution to the second order ordinary differential equation is well known. Is we already studied in engineering and mathematics class. The general solution is given by sine combination and sine and cosine, and then here factor k here, and then here the C1 and C2. These two are integration coefficient. And then let's consider boundary condition here. At x is equal to 0, v naught is equal to 0. Then v naught is equal to 0. V naught is what the first term, the sine 0 is equal to 0. And then here C2, cosine 0 is equal to 1. That's why we can conclude that C2 should be equal to 0 because of this. And then let's consider the boundary condition. Second boundary condition says that the VL is equal to 0. And then if you put VL is equal to 0, C1 times sine KL is equal to 0. So if C1 is also equal to 0, let's say C1 and C2, these two are equal to 0. Let's put C1 is then V is equal to 0. So let's put V is equal to 0. then this governing equation is naturally satisfied, isn't it? But this is trivial solution. This condition is exactly same as for the first configuration. There is no buckling. The problem can be studied by using the one-dimensional theory. The stress is simply P divided by the cross-section area. But if we have a non-trivial solution, then how do you achieve the non-trivial solution? Here we already know that C1 should be equal to 0 to satisfy the boundary condition. Then how do you satisfy the second boundary condition having non-trivial solution? Instead of C1 is equal to 0, and then this second part, this part should be equal to 0. Then we can obtain the non-trivial solution. Then because this is a sine function, sine KL, if sine KL is equal to 0, then how can we make sine KL is equal to 0? So if KL is equal to, as it given here, the integer times the pi, then this is equal to 0. Actually, we don't determine what is the value of this integer. The n can be 1, 2, 3, any numbers is okay. Then once KL is n pi, then because we already discussed, we already let the k square is p over e, then square p over ei is equal to n pi. So let's square both sides, then we can calculate the load p. So once load p is equal to this value, then the column buckles. That's the meaning of this solution. So make sure that then how do you measure the magnitude of lateral displacement? So make sure that magnitude of lateral displacement cannot be determined by this simple discussion. So it discussed only the condition for buckling. Okay, to determine C1 value here, so we need to carry out the large deformation analysis. This is much more complicated, and then this is out of scope of mechanics of material class, and then also the out of scope of our discussion in undergraduate courses. Okay, now let's talk about buckling mode. Let's say this is a solution to this problem. As I told you, C1 is not determined. Okay, we cannot determine. Not determined by this analysis, but we can understand the overall shape of the solution. The overall shape of the solution is given by sine times n pi over L and x. This n is equal to 1. N is equal to 1. Then if x is equal to 0 is 0. And then x is equal to pi over 2. No, pi. X is equal to, no, L, sorry. The x is equal to L sine pi over L times L, then sine pi, this is equal to 0. So this is when n is equal to 1, we have half sine curve. Okay, the the first order the buckling shape. This is the first buckling mode. Then if you consider n is equal to 2, then we have a double curvature in the length of the column. This is mode 2, the second mode. But if you calculate the amount of buckling load, the P1 is much smaller than the mode 2 load value. That's why in most cases, so we have mode 1. So practical importance is mode 1 problem, okay, the mode 1 solution. So typically we use the mode 1 solution, and then the mode 1 load is called Euler's buckling load. And then as I mentioned, the Euler's buckling load is for the first mode. The n is equal to 1, and in the place of n is we put the n is equal to 1. But depending on the boundary conditions existing in the middle of the structure, for example, to achieve the second mode, so we need to put intermediate support here. Then we can achieve the second mode of the buckling. Okay, then what's the stability condition here? Stability condition is very easy. If the load P is less than the critical load for mode 1 buckling, then this is stable. Then our analysis is by the one-dimensional analysis. And then if load P is greater than the critical load, then it's unstable. Then my deformation becomes another, should want to find another equilibrium positions. So we cannot analyze the problem using one-dimensional solution. So we need another tool to investigate this situation. Okay. So it's like the issue regarding the shear center. What is the do you remember what is the reason that we discussed the shear center? Because we use the beam theory to investigate stress development of inner beam. But if you apply load in arbitrary direction, in the lateral direction, then it's going to produce torsional moment. Because we are using the beam theory, so there is no way to handle this torsional moment, isn't it? That's why we need to find the right position to apply the load, not to cause any torsional moment. That's the issue regarding the determination of shear center. But here the buckling too. So if my load exceeds the buckling limit, then the stability limit, then we have buckling. Then my analysis is not enough to use only one-dimensional problem. That's why we don't want to have the situation the P is greater than the buckling limit. Okay. So now let's try to calculate the stress value. For example, the first stress is plasticity limit, applied force P divided by area. This is the plastic limit. And the second one is stress P critical buckling load divided by cross-section area. This is given here. The critical stress value is, P critical divided by the area is given by this equation. So if you look at this equation carefully, and then critical stress is inversely proportional to the length square. That's why it naturally have this curve here. So then in our analysis, we have to check two different, the safety limit. The first one is the plasticity limit. The stress should be controlled less than the yield strength value. Okay, less than the yield strength value. And the second one is the stability limit. My length of structure or the load level should be controlled. The stress level is less than the stability limit. My safety limit should be here, isn't it, right? This is the safety domain. If my stress value is, out of the safety domain, this is not safe. Here, above here, this is failed by the plasticity, and then failed here, it is failed by the stability. Is it clear, right? And then here, we'd like to introduce a new variable, so-called radius of gyration. This is useful for the discussion of stability. The square root of second moment of inertia divided by cross-section area. This is the radius of gyration. So if you open design of steel structures, you can find this radius of gyration in many different places. Typically, this buckling issue is more important in design of steel structures because steel structures are slender. Okay, slender. Sorry, slender. What I mean, we are using long thin members. Okay, long thin members. Then it is long thin members because the stability, the critical stress is proportional to L, inversely proportional to L square. And then if it's so thin and long members, then less critical stress value. Okay. Okay, now let's talk about the effect of boundary condition.